And we're back. Today we're going to talk about the ideal gas law, which combines the three gas laws that we've already talked about. So we've already talked about Charles' law, the fact that volume and temperature are directly related. And then Avogadro's law, that volume and amount, volume and number of moles, are directly related, along with Boyle's law, which you saw in the lab, in which those, volume and pressure, are inversely related, assuming that all of the other variables are constant. And the reason why this law is called the ideal gas law is that we're assuming the gases are behaving ideally and not like real gases, and we're going to talk about this difference later in this unit. So real gases, we know those molecules, first off, have actual volume. Those individual molecules take up space, and they all attract each other. So when talking about the ideal gas law, we are ignoring those two facts. Okay, and when you combine these three laws, you will get the fact that volume is equal to R, which is some constant, combining these constants of B, A, and K, and that's times T to N, T being temperature, which has to be always in Kelvin, N, which is moles, and divided by volume, which will always be in liters. And these units are important when we look at the rearranged ideal gas law. So usually when you see the ideal gas law, it's PV equals nRT. And if you look at that constant R, which will always be given to you, it's 0.08206. And if you look at those units are always the same. So that means your volume always has to be in liters. So if your volume is in milliliters, it has to be converted to liters. Same thing for pressure, it has to be in atmospheres. So if it's in torrs or pascals, you have to convert it to atmospheres. Moles is always moles, and still always temperature has to be in Kelvin. Okay, so using this ideal gas law, we can solve for any one of these four different variables: pressure, volume, moles, and temperature. And if you know 3 out of the 4, automatically you can get the fourth one. Okay, so looking at this first example, we want to determine the number of moles of the air in a tire on a car. So we are solving for N, so rearranging the ideal gas law, PV equals nRT. If we're solving for N, we take PV over RT. And looking at all our variables here, we have 3, it's asking for the fourth, so that's how we know we're using the ideal gas law. And identifying these variables should be easy. So the automobile tire at 23 degrees Celsius, so that's temperature. And we know always the temperature has to be in Kelvin. So we add 273, so the temperature in Kelvin is 296. Next, the internal volume, 25.0 liters. We don't need to convert that since it's already in liters, and the pressure, P, is already in atmospheres. Okay, so now that we've labeled each of those, we just plug those into our formula. And in your calculator, be careful when using the order of operations. Make sure your denominator is always in parentheses. And do also be careful with the R, with the ideal gas constant, with the universal gas constant. Do not forget this 0. It's 0.08206 and not 0.8206. And you'll notice when using this universal gas constant, all of the units will cancel besides the one you are solving for. So all the units cancel except for number of moles, which makes sense because that is what you are solving for. So when you do all this, you get 3.27 moles. So that's our correct answer. Also, if it instead have asked you what is the number of grams of air in the tire, if you were given an actual element or compound, you should easily be able to convert from moles to grams, since you would know the molar mass of the compound. The only tricky thing there is, let's say ask you how many grams of oxygen would fill this automobile tire. Remember, oxygen is one of your diatomic molecules, so you would have to use the molar mass not just of oxygen, but of O2. So remember, your diatomics are hydrogen, oxygen, nitrogen, and also those in group 17. Okay, so that's if solving for a number of moles. And now we want to know what's the pressure in a 304.0 liter tank. So that's volume that contains 5.670 kilograms of helium at 25 degrees Celsius. And once we see that degrees Celsius, we know we have to convert to Kelvin by adding 273, so we get 298 Kelvin. So here, it's asking for pressure, and our other variable is mass instead of moles. Right? But we know we can easily get from mass to moles by dividing by the molar mass. Okay, so we already know kilograms to grams. There's 1,000 kilograms. Excuse me, there's 1,000 grams in 1 kilogram. So 5.670 kilograms is equal to 5,670 grams. And it says of helium, so here it's giving us that element, that gaseous element. And we know from our periodic table, for every 4 grams of helium, there's 1 mole. That's the molar mass of helium. So when we do that, we now have our number of moles of helium. So now that we have the number of moles, now we can use the rearranged ideal gas law, PV equals nRT. Now, since we're solving for pressure, it becomes nRT over V. So now we have each of our variables. We plug each of them in. And you'll notice, still with this universal gas constant, all of these units will cancel besides the one that we are solving for. Okay, so we're left with atmospheres. That makes sense since we're solving for pressure. And here for our final answer, we get a final answer of 114 atmospheres. Okay, so you should be able to use this ideal gas law for any of these variables, and you should also be able to use this for 2 different states. So add this to the back of your notes. So if we have 2 different states of the ideal gas law. Okay, so let's say we have a sample. Oops. A sample contains 0.35 moles of argon gas at 13 degrees Celsius and a pressure of 568 torr. So that's one state. Then it says that sample is heated to 56 degrees Celsius and a pressure of 897 torr. And we want to know what is the change in volume between these two states. And you'll notice here, for this second state, I did not give you the number of moles. So for this one, we are assuming the number of moles is staying constant. Okay, so what we can do for this first state is solve for volume using the ideal gas law. So nRT over P for this first state. So we know there's 0.35 moles. We'll use our value of R, 0.026, 08206, and then the temperature in Kelvin, so 13 plus 273 is 286. And I left off all the units here, but remember all of the units should cancel out besides those 4 liters using the universal gas constant. And all here we had units of torr for pressure. So that means if we want to convert to atmospheres, we have to divide by 760. Okay, so doing all that, we get a volume of 11 liters. Now for the second state, we're still using the same rearranged ideal gas law. And remember we said it's the same number of moles. R is always constant. But now we have a new temperature, 56 plus 273, which is 329 Kelvin. And same thing here, our pressure is in terms of torrs. So that means we need to convert that to atmospheres by dividing by 760. When we do all that, we get a volume of 8.0 liters. So that means the final volume minus the initial volume, 8 minus 11, that change in volume is negative 3 liters. And that negative indicates that that volume is decreasing by 3 liters. Okay, so you should be able to use the ideal gas law when given 3 out of the 4 variables for 2 different states, and then be able to calculate the difference between those 2. Okay, so the ideal gas law is a combination of all of those different laws in addition to the combined gas law. So also add this to the back of your notes. The combined gas law combines those variables for pressure, volume, and temperature, but not for amount, not for number of moles. So the combined gas law is P1 V1 T1, P1 V1 over T1 equals P2 V2 over T2, and still making sure your temperature is in degrees Celsius. Okay, so let's say here we want to know what temperature, and notice it says in degrees Celsius. So we're going to get our answer in Kelvin and then just have to convert back to degrees Celsius. You cannot just keep this other temperature in Celsius and then as a result get your answer in Celsius. You have to convert this to Kelvin. So 27 plus 273, and you get a temperature of 300 Kelvin. And you'll notice here both of these volumes, the initial volume V1 and the final volume V2, are both in milliliters. If we were using the ideal gas law, you would have to convert these. But since we're not using R, since we're not using the gas constant, you do not have to convert them to liters since they are the same unit and will cancel out. And same thing here for our initial P1 and P2. Both of those are in atmospheres, so we do not need to cancel them. But in this case, if we're using the combined gas law. If they were both in torrs, we would not have to convert them since we're not using our universal gas constants, since we're not using R. Okay, and for the combined gas law, you should be able to solve for any one of these variables, P2, V2, T2. So in this case, we're solving for T2, so you should just be careful. I think the combined gas law is the trickiest to rearrange, so you have to be careful when doing that. So if we're solving for T2, move it to the other side of the equation. So we have P2, V2, and we move T1 to the other side. So that all goes in the numerator, and then you just have to divide both sides by P1 and V1. And now, since we labeled all of the variables, now we just plug them in. And this one, it should be obvious you're using the combined gas law and not the ideal gas law, since you're not given number of moles. Okay, so here P2, 1.40 atmospheres, our V2, 293 milliliters, and our T1 is 300 Kelvin. And we divide by P1, 1.05 atmospheres times our initial volume, 121 milliliters. And when you do all that, you get a temperature in Kelvin of 969. And remember, it said at what temperature in degrees Celsius, so that means we have to subtract by 273. So as a result, we would get a temperature in degrees Celsius of 696. All right, that's all for today. See you next time.